You know, for the longest time, quantum computing felt like something straight out of science fiction, right? Well, not anymore. We are officially entering the practical era, a time where these unbelievable machines are actually being built to solve problems we once thought were literally impossible. So today, we're going to break down exactly how IBM is leading that charge. The whole conversation in the quantum world has just completely flipped. Seriously. It's not a question of if we can build a useful quantum computer anymore. We can. The real questions now, the ones everyone is focused on, are how do we build them? How do we scale them up? And, what do we do with them to tackle the huge challenges in chemistry, finance, and material science that are just way out of reach for even our best supercomputers?
And that shift brings us to what might be the single most important concept in this whole field right now: quantum utility. This isn't just about building a quantum computer for the sake of it. It's about reaching the point of true quantum advantage. It's that tipping point, that moment where these machines start giving us answers to real-world problems that are better, or faster, or heck, even possible, when a classical computer would just give up. That's the finish line we're all racing toward.
Now, to get to that finish line, IBM took this really fascinating two-pronged approach to designing their processors. You can think of it like a strategic fork in the road, a decision that really came down to one fundamental question: should we build bigger or should we build better? Okay, so on one side you had the scaling branch. This was just pure raw ambition. It was like a brute force approach to see how many qubits they could possibly pack onto a single chip. It was all about solving these huge engineering puzzles, like how do you even wire up more than 1,000 of these things? But the other path, the performance branch, that had a totally different philosophy: quality over quantity. The focus wasn't on having the most qubits, it was all about having the best qubits, the most reliable, the most stable, and the most free of errors.
And that scaling branch? Wow, it peaked with the Condor processor, a chip with a frankly staggering 1,121 qubits. But here's the twist, and it's a big one. Condor was never meant to be the final answer. It was this brilliant engineering experiment, a testbed that taught IBM so many crucial lessons about density and manufacturing. But the real path to utility? Well, that lay down that other fork in the road. And this slide right here shows that pivot perfectly. Meet Heron. This is the star of the performance branch. Now, compared to its predecessor, Eagle, the goal wasn't just size. It was pure performance and super low noise. The secret weapon? A feature called tunable couplers. The best way to think about them is like tiny, ultra-precise little switches between the qubits. They let engineers turn the interactions between them on and off, which dramatically cuts down on interference. And the result? A massive 3 to 5 times reduction in errors. This was the breakthrough.
Of course, a world-class processor is pretty useless if it doesn't have a world-class home. And let me tell you, a quantum processor needs an extraordinary one. This is IBM's Quantum System 2. It's really less a single computer and more of a blueprint for the world's first ever quantum data center. This thing is just an absolute marvel of engineering. I mean, look at it. It's this huge hexagonal structure, 22 feet wide, and it houses multiple Heron processors inside. It's also designed to be modular, so you can actually link them together to scale up. But the part that really blows my mind is the environment inside. To even work, these qubits have to be kept at 15 millikelvin. That is colder than the vacuum of deep space. So how on earth do you get something that cold? Well, it's basically this 4-step cryogenic dance. First, powerful pulse tube coolers do the heavy lifting, getting the system down to 4 Kelvin. Then you've got these special ribbon cables that deliver all the control signals without leaking in any heat. Next, you need incredibly sensitive amplifiers to boost the super faint signals coming from the qubits so we can actually read them. And finally, the whole thing is magnetically shielded to protect those delicate quantum states from something as simple as a passing cell phone signal. Yeah, really.
But here's the thing. Even with the best hardware and the most insane cooling, quantum computers are incredibly fragile. The single biggest enemy in this entire field is what we call noise. These tiny, random errors that can creep in and just completely wreck a calculation. This is where the other half of the revolution comes into play: software. It's the digital magic that makes today's imperfect hardware genuinely useful.
So there are basically two main software strategies for fighting this noise. On one hand, you have error suppression. This is proactive. The best analogy is noise-canceling headphones. It uses clever physics tricks during the computation to stop errors from ever even happening. On the other hand, you have error mitigation. This is reactive. Think of it like editing a grainy photo after you've taken it. It lets the errors happen, but then it uses powerful classical computers to analyze the noisy results and figure out what the perfect, noise-free answer would have been. Now, to make all this super easy for developers, IBM's Qiskit software bundles these techniques into simple resilience levels.
So level 1 is kind of your basic cleanup crew. It just corrects simple readout errors. Level 2 gets way smarter. It actually runs the calculation multiple times with different amounts of noise, and then it extrapolates backwards to predict what the perfect zero noise result would look like. It's really clever. In level 3, that's the most powerful, using some very advanced math to basically rebuild a perfect answer out of a whole collection of flawed ones.
So you take this amazing hardware, you pair it with this incredibly smart software, and what do you get? You get a clear path forward. IBM has laid out this incredibly ambitious public roadmap, and it charts a course from the utility-era machines we have today, all the way to what's known as fault-tolerant quantum supremacy. All right, so let's walk this roadmap. Right now, in 2024, we're running circuits with about 5,000 quantum logic gates, and you can think of gates as the basic operations in a quantum calculation. By 2026, the goal is to show, for the first time, a quantum machine beating a classical one on a truly meaningful scientific problem. But the huge leap comes in 2029 with a system called Starling. This will be the first system with built-in error correction, making it fault-tolerant. Then, by 2033, the plan is to have Blue Jay, a system so powerful it will fundamentally change how we think about supercomputing itself. And if you want to really understand how massive that leap is, just look at this. We are going from running circuits with 5,000 logic gates today to 100 million gates by 2029, and then to a mind-blowing 1 billion gates by 2033. We're not talking about a straight line of improvement here. This is an exponential explosion in computing power.
Okay, but what if this timeline could actually get faster? Well, a recent software breakthrough in error correction could be a total game changer. See, the old thinking was that you'd need maybe thousands of these messy, error-prone physical qubits just to create one single perfect, stable, logical qubit. But these new methods suggest we can do it with far, far fewer. This could dramatically speed up the whole roadmap, bringing those billion-gate systems into reality much sooner than anyone expected.
So when you put it all together, the processors, the cooling systems, the software, the roadmap, it's all leading to a future where we have a machine with 1 billion quantum gates at our fingertips. And that brings us to one final, just thrilling question. When we have the power to solve a problem that has always been impossible for humanity, what should we solve first? Designing brand new medicines? Creating new materials for sustainable energy? Unlocking the fundamental secrets of the universe? That's what's really at stake.